So today we're going to start 8.2, but really talking more about the central limit theorem and what it actually means to look at a sampling distribution. But before, I want to kind of go back to what we did yesterday with the sampling distributions. I'm only going to do one of these, even though there's 3 on the sheet, because I think you'll get the idea from one. So let's pretend our sample set is 0, 4, 8, and 12. So originally, if I put that data set in my calculator, and I do my one variable stats, I get a mean of 6 and a standard deviation of 4.472. So my mean is 6, the standard deviation is 4.472. Notice I'm using sigma. We're assuming this is a whole population. Now I'm going to go through and generate a sample size of 2. So again, we're going to pick with replacement just like we did yesterday. So 0, 0, 0, 4, 0, 8, 0, 12. I could pick 4, 0, 4, 4, 4, 8, 4, 12. 8, 0, 8, 4, 8, 8, 8, 12. 12, 0, 12, 4, 12, 8, 12, 12. So then when I go to find the mean, I have 0, 2, 4, 6, 2, 4, 6, 8, 4, 6, 8, 10, 6, 8, 10, 12. So this is my sampling distribution of size 2. Now, if I put that in my calculator, because that's my sampling distribution of size 2, so I'm going to go into list 1, put all of those numbers in. You'll see what ends up happening to the mean and the standard deviation. Hopefully I got it right. So when I go to do my variable stats, the mean, you'll notice, stays 6. So x bar stays 6. So the mean of the sampling distribution of size 2 is the same as the population mean. But notice sigma. Sigma x is now 3.162. What that really is you take your population mean and you divide it by the square root of your sample size. So if I took 4.472 and then I divided it by the square root of 2, there's my new sample mean. So that's kind of what 8.2 starts with. We're not going to do the rest of them because you kind of get the idea and it becomes tedious. So here are general properties of your sampling distribution of a sample mean. So x bar is the mean of the observations in a random sample of size n from a population having a mean of mu and a standard deviation of sigma. Denote the mean value of x bar, the distribution, by the mean mu of x bar and the standard deviation of the x bar distribution by sigma x bar. So here's what it means. So mu of x bar is equal to mu. So in words, that means the mean of your sampling distribution is equal to your population mean. So notice in this original one, the mean didn't change. It was still 6 for either one. Sigma of x bar is equal to sigma divided by the square root of n. So the standard deviation of the sampling distribution is equal to the population standard deviation divided by the square root of your sample size. Okay, these two are on your formula sheet, so you don't have to memorize them. And on our new formula sheet, what you have to do is flip to the, so we've been working on this front page, so now we're in Inferential Statistics, like I said. Flip to the back, and if you look at the mean right here, so for one population, Right there, the mean of the x bar is equal to the mean, and here's your standard deviation. We'll get to this later when we get to chapter 9. But these are your two things right here, so for one population. Other properties of the sampling distribution, when the population distribution is normal, the sampling distribution is also normal for any sampling size. So like SAT scores are a normal distribution. They're a bell curve. So if I take any sample size, I should get a normal distribution. What happens if it's not normal? That's what the essential limit theorem says. So we're going to write it out, and then I'm going to talk about it. So the essential limit theorem says, when n is sufficiently large, talk about that later, the sampling distribution of x bar is well approximated by a normal distribution even when the population distribution is not normal itself. So we're going to do a lot in chapters, like later chapters, chapter 9 through 12, where we're not necessarily going to come from a normal distribution. So we're going to talk about the essential limit theorem and what does n being sufficiently large actually mean. There are certain rules, but this is what the essential limit theorem says. If you don't have a normal approximation distribution, as long as you can get a sample size that's large enough, you can make it normal. So rule number 1 describes the center of the sampling distribution. Rule number 2 describes the spread. So kind of here's the math behind the mean and the standard deviation. You do not need to know this, but this is just the math all kind of worked out, kind of how it comes from, because you're combining random variables because you're taking a sample size, obviously. So don't worry about these, just stick with the top. Rules 3 and 4 describe the shape of the distribution of x bar is always normal or approximately normal when the population is normal or the sample is large. And rule number 4 says n needs to be sufficiently large. How large is large? It does depend on the original population. If it's close to normal, n need not be large, but if it's very non-normal, n needs to be bigger. So in general, the central limit theorem can be applied if n is greater than 30. N should be greater than 30 when we're doing these. So let's try some examples using the central limit theorem. So suppose the weight of apples have approximately normal distribution with a mean of 200 grams and a standard deviation of 35 grams. So part A, this is a chapter 7 question. This is what we used to do. What's the probability that if you choose one apple at random, its weight is at least 220 grams? So probability x is greater than 220. So this is what we did in chapter 7. This is where n is 1. Okay? So what we would normally have to do, we find a z-score. So that should be greater than 220 minus 200 over 35. So let's see, 220 minus 200, divided by 35. Can't do it today. Gives me a z-score of 0.57. So I'm trying to find the probability z is greater than 0.57. Now remember, when we do a greater than, we can't do a greater than in our formula sheet. So I'm going to do 1 minus the probability z is less than 0.57. And if I go to my formula sheet, 0.57, 0.7157, so 1 minus 0.7157, .2843. Now I know there are some of you that like to use the calculator. So the other way to do this is we do normal CDF. We're doing greater than 220, so 220 is my lower bound. We'll do infinity for the upper bound. 200 is my mean, and 35 is my standard deviation. So remember, when you're doing this, I don't care if you do it, but you need to label. Now, most of you, if you go to your distribution menu, I have an 83, so mine's going to look kind of like this, but yours should prompt lower bound, upper bound. So we're going to do 220, comma, a bunch of 9s, 200, 35. So 0.2839. So a little bit off, but I usually have both written on my answer key, and so will the AP guide. So you can do it either way. So this is what we used to do. This was Chapter 7. Part B is a Chapter 8 question. So now we're getting into, okay, well here's now we have a sample. What's the probability if you choose 25 apples at random that the average weight is at least 220? So now n is 25 instead of just 1. So the only thing that's going to change, we had to come up with a new mean and a new standard deviation, because now we have a sampling distribution. So again, the mean stays the same. If it's 200 grams to begin with, it's going to stay 200 grams. But the standard deviation is going to be 35 divided by the square root of 25. Okay, so 35 divided by 5. So our new standard deviation is 7. And we'll kind of talk about tomorrow why you'll notice the standard deviation gets smaller. We'll talk about that tomorrow. Today I just want to show you the difference between a Chapter 7 question, Chapter 8 question. So it's kind of set up the same. We're still looking at the probability x is greater than 220, but instead of just one apple, we're looking at 25. So we're looking at the average weights. Now we're looking at x bar is greater than 220, because we're looking at a sample of 25 versus a sample of 1. So that's the same as the probability that z is greater than. So now we got to do a new z-score. 220 minus 200. But this time we're going to divide it by 7 instead of 35 because we got a new standard deviation. So now I'm looking at the probability z is greater than 2.86, we'll round to. So same process. I got to do 1 minus the probability z is less than 2.86. So if I go to 2.8.9979, 1 minus 0.9979, I get 0.0021. Now if I wanted to use the calculator, again, normal CDF, 220 is our lower bound, infinity is our upper bound, 200 is our mean, but again, our sigma is going to change to 7. I wrote sigma instead of 7. So the only thing that changed was sigma. So if I do that in my calculator, give a normal CDF, so 220, comma, a bunch of 9s, 200, 7, 0.0021. So you get almost the same answer. So, and we'll talk about tomorrow why the probability goes down and why it goes down so much. That's kind of day 2. But today, I just wanted to show you, so this is what we used to do. We had one apple, we were looking at one thing. Now we're looking at a sampling distribution, so just really the standard deviation changes.